Okay, I'll start the live stream. I think start in a moment. Okay, so everyone, welcome. Today we have our fourth session of student presentations, and we're going to start our session with Ivan, and let Maria, his mentor, introduce you.
So Ivan Gutierrez is a bachelor student at the Department of Computer Science at ETH Zurich. His research interests are in computer architecture, but also in machine learning and security when applied there. And he is going to present the paper GPUHammer, Rowhammer attacks on GPU memories are practical.
Good afternoon. Today I'll be presenting GPUHammer. It shows that Rowhammer attacks on GPU memories are practical. Let me start with an executive summary of the paper. There has been a surge of GPU deployments in the cloud due to an increasing demand for machine learning. But despite of that, there has been no prior paper that studies the vulnerability of GPU memories for Rowhammer, which is a DRAM vulnerability exploit. And the main problem is that due to several differences to CPU DRAM, there's major challenges to actually get Rowhammer on GPU memories too. And the goal of the paper is to explore the potential for Rowhammer attacks on GPUs, specifically NVIDIA GPUs, because they have the largest market share. The key ideas the paper goes over is how to solve the GPU DRAM specific challenges, like mapping the virtual memory addresses, which are proprietary and unknown on GPU, using timing differences, overcoming the latency and faster refresh caused by the focus on high bandwidth, and defeat proprietary in DRAM defenses. So the structure of today, first, the result of the paper is the first successful Rowhammer attack on GPU. They demonstrated several bit flips on an NVIDIA A6000, and they caused catastrophic accuracy drops on different machine learning models. So the structure of today's presentation will be that first I'll give an overview on the technical background. Then I'll go over the key challenges and the ideas on how to solve them. Afterwards, we'll look at the results. Then the conclusion. Afterwards, I'll give my opinion on the paper, and finally, we'll have a discussion. So to start with the technical background, how does a GPU even work? And basically, a GPU is an accelerator that's built specifically for executing a huge amount of threads in parallel. So its strengths are things like matrix multiplication, image processing, and of course, machine learning. Then the paper focuses on NVIDIA Ampere specifically, mainly the A6000, but also the A100 and the RTX 3090. Those are all from the same Ampere microarchitecture. And such a GPU is made up of multiple streaming multiprocessors. Those would be located here in the silver area at the center. And the A6000, for example, has 80 of those streaming multiprocessors, and each of them executes a huge amount of threads in parallel. And the streaming multiprocessors are made up of multiple blocks of warps. And what are warps? A warp is a group of 32 threads, and they all execute the same instruction in lockstep, which means all of the threads have to wait until everyone is done. And then the warps within a block execute in a time multiplex manner. This means that they can do different things asynchronously, like they're not in parallel, but while one warp is, for example, waiting for memory access, the other one can already do something new. And now for the DRAM architecture itself, which will be the focus, the NVIDIA GPUs use GDDR, which is in concept very similar to the CPU DDR, but there are some differences that we'll go into. There's also HBM, which is the 3D layered version, but its layers are similar to GDDR. And for each bank, you have basically the same structure as in normal DRAM. You have multiple rows, and to access a row, the memory controller has to first activate the row into the row buffer. Then in the row buffer, you can read or write something, and then as soon as you want to access a different row in the same bank, you have to pre-charge it, which means to close and then wait for a predefined time. And the A6000 specifically has 46,000 rows per bank, and then 16 banks in a single chip. And yeah, I forgot to mention it earlier, the DRAM chips are actually the ones you can see here at the side of the processor. And well, the multiple banks per chips are either accessed by one 32-bit channel, or you can split them up to two 16-bit channels, but in the end you have 16 banks per chip and 12 chips in total per in the GPU, and the focus is high bandwidth. The A6000 has a bus capacity of 384 bits, so you have a higher latency and a fast refresh rate of below 32 milliseconds, while CPUs usually have up to 64 CPU DRAMs. And now, what even is Rowhammer specifically? It's a vulnerability in DRAM where you repeatedly and quickly activate the aggressor row, here the one in black, and this causes its charges to leak and cause bit flips in the victim rows that are in orange here. And there are several mitigations that have been researched, like target row refresh, which tries to detect rows with suspicious activity and preemptively refresh its neighbors. But that and even more sophisticated mitigations can still be bypassed, as shown by related work. So it's an ongoing problem. And now the motivation of this paper is because the GPUs are a backbone of machine learning models, and NVIDIA specifically has a 90% market share. And there is an increasing demand in the cloud. Also, the GPUs are often shared, so it would be important to explore the full threat model, because the machine learning models in the cloud face several vulnerabilities, but no one explored if they are also vulnerable to GPU memory attacks, which could be catastrophic because modern models have gigabytes of weights in the memory, like the large language models have several dozens of gigabytes. And a single bit flip could already be catastrophic and ruin the predictions of other users on the same GPU. So the goal is obviously to explore if NVIDIA GPUs are vulnerable to Rowhammer, but also if there's a realistic exploit you can do with that vulnerability. Then the paper also discusses possible mitigations. And also we assume a specific threat model, namely the GPU is shared in the cloud between multiple tenants. Specifically, it's with time multiplex execution, which means that all 250 milliseconds it switches between the users, but the memory is often not refreshed between the users, so it can keep the state. And 250 milliseconds is usual for such setups. And they also assume that error correcting codes are disabled. Those could detect single bit flips and correct them, but they cause up to 10% slowdown, so it's often disabled by default. And also they assume that the attacker can execute CUDA kernels natively with user level privileges, which is also usual for such setups. And now we'll go over the challenges they had to solve for GPU memory specifically. The first challenge that often poses it for accessing the rows, you first have to evict the row from cache because it might be stored there. But on this GPU architecture, it's not a problem because we are provided with the discard instruction. But on different GPUs, that might not be the case. But to actually access the memory row, you also have to evict it from the row buffer where it might be opened already. So you need to access a different row and create a conflicting access. But the problem is that since we don't know the virtual address mapping to the actual row locations because it's proprietary, we can't just do that. It's not even exposed to privileged users as opposed to in CPU-DRAM, so that's a key problem. The next thing is that we need enough activations, like a very high hammering rate, usually 10,000 activations for a row, to actually get bit flips between refreshes, but the refresh rate is twice as high, like 23 milliseconds on the A6000. And we also have 5 times the latency, which is 300 nanoseconds versus 60 nanoseconds usually. And the third challenge is that there might already be proprietary in DRAM defenses that we don't know about, and we would also have to bypass those to actually get a bit flip. And now, how do we solve the first challenge with the virtual address mappings? We try to reverse engineer them, and for that we can exploit a specific difference in latency, because as soon as you try to access 2 addresses in the same bank, you have a row conflict, and therefore you have to wait a while until it closes and then opens again. So with the timing differences, you can find out if 2 addresses are in the same bank or not. And what they do specifically is they allocate an array, almost the maximum size of the entire memory. Then they pick a reference address and they collect all addresses that take longer to fetch. So they have a conflict and therefore it's in the same bank. On the graphic to the right, you can see how you have 2 threads. And first you discard it from cache. And then, because the 2 threads are in lockstep, you have accesses to the bank, but they return at the same time because they have to wait for each other. But you know, if the entire process of accessing 2 memories at the same time takes longer, then it has to be 2 addresses from the same bank. And if it takes shorter, they're in different ones. And after you've done that, you can compare all the conflicting addresses with each other to find duplicates, like there might be addresses that map to the same row. And when you filter those out, you have the ones that actually map one address to one row. And they also noticed that the addresses itself changed across runs, but the offset within the allocated array remained the same, so you can still do organized patterns. And now to the second problem with how do we overcome the higher latency and faster refresh. If you try to have a single thread, it's not enough at all because you only have 100,000 activations. And if you have multiple aggressors to bypass things like target row refresh, which, yeah, I should have mentioned it earlier, the target row. No, I did mention it. You have to have enough aggressors to overwhelm the detection of suspicious threats. But if you have 20 aggressors, you only have 5,000 per row, which is not enough at all. So, of course, you can have multiple threads. On the diagram on the right, you see how first in a single thread, you have one access and then a lot of idle. And that's not enough at all. In the middle, you see how you can have multiple threads. And then you can do multiple accesses at the same time. But each time, you have to wait until the address returns. And because all the threads wait for each other, you have some users idle, because in this, you could already request new accesses. So the idea they had is to use threads across different warps, because then while one warp is waiting for its turn, the other one can already schedule access to the memory controller. And here in this chart, we can see how a single thread only reaches 100,000 activations. With multiple threads, you need around 30 to reach maybe 500,000 activations, but with different warps, they already reach 620,000 activations with only 8 aggressors, which is very close to the theoretical maximum of 700,000. And finally, how would we bypass in DRAM mitigations? We can try and synchronize the aggressors with the refresh by inserting delays to escape the mitigations like target row refresh. And here on this graphic, you can see how we would align the multiple aggressors such that they attack simultaneously, and then you would insert a delay such that the memory controller can refresh normally. And the reason why you have to synchronize the different aggressors is if you don't have them all hammering at the same time, it could happen that even though you have even though you have a lot of aggressors, the mitigation could still prevent all of them, because they could happen at different times and it would detect them at different times. But if you have them all hammering at the same time and in the same order, it's already overwhelmed in the same way every time, so you can consistently overcome the mitigation. So yeah, we have synchronized hammering between refreshes. And the reason it's gaps and not, for example, a synchronized threads instruction is because the ordering wouldn't be always the same. So we couldn't predict if the pattern works consistently. And they found out that up to 8 warps synchronized well, and above that, they didn't manage to synchronize it. And in this plot, you can see how different amount of delays, which were implemented with add operations, synchronized and reached consistent hammering between the refreshes. Like in blue, you have 8-sided attack, and the green one is 16-sided with 8 warps and 2 threads, and the red one is 8 warps times 3 threads. Now to the results of the paper. The experimental setup was that they ran a systematic hammering campaigns across 4 DRAM banks. They didn't do all the banks because each bank already took 4 hours to reverse the address mapping. And that would have taken too long for all the banks, but they did it for 3 different GPUs. And they hammered for 3 hours per bank with ECC still disabled. And they used the row sets that we got from IDEA 1, the high-intensity hammering kernels from IDEA 2, and the synchronized n-sided hammering from IDEA 3. And also, they hammer for 128 milliseconds, which is about 5 refresh cycles. And the aggressors are 4 rows apart, and after that time, they increment by 3 rows. And the result is that here the rows are the different GPU banks. And as you can see here with 20 and 24 aggressors, they managed to get bit flips. With 24, there were bit flips on every single bank on the A6000 GPU. Sadly, the other GPUs didn't show any bit flips at all. And the exact reasons why that is are hard to know. The paper itself leaves it up to future work to explore the reasons and approaches on how to get those to flip to. But what they also notice is that the aggressor row is always on one side, like it's never from both sides. And that's weird because you would think that if you hammer from 2 sides, that would be more effective. But another thing that appears weird is that the rows that are more efficient, or if the aggressor row is with one row in the between, like it's not the immediate neighbor. And that suggests that the memory layout might actually be non-contiguous. Next, we can see the threshold for the different bit flips. And the lowest threshold was 12,000 activations, which is close to the usual 10,000. But for some banks, it was closer to 15 or 16,000, which means that there might be differences between how the banks are structured microarchitecturally, or also between specific locations within the banks. And finally, we can see that with below 17 aggressors, there actually weren't any bit flips. So that confirms our assumption that there has to be a TRL-like fixed size sampler that can only track 16 rows per bank. And as soon as we have more than that, it's overwhelmed, so we can actually perform bit flips. And finally, we see that most of the bit flips were from 0 to 1. As you can see, the rows are the different bit flips, and here in this column we see the direction. And also the location is mostly the 0th, 6th, or 7th bit. Now for the actual real-life exploit, they again assumed the time-sized multi-tenant setting with 200 millisecond sizes and ECC still disabled. And they also had to use memory massaging, which means that you allocate a large array within memory, and then you free a chunk where you know there are flippy bits. And because the memory managers that are usually used in such time-sized settings are optimized for high performance, it doesn't think twice about directly reallocating the freed chunk for the next user. So you know that the victim will allocate their memory in that region. And here you see a table of different image categorization models, with the first column being the base accuracy and the second column being the accuracy after bit flips. And you can see in the upper part for the bit flips D1 and D3, which were both in the fourth bit of the exponent of the floating point 16 exponent, we can see a relative accuracy degradation of 99%. For example, here it went from 80 to 0.02%, and that's really catastrophic. And the reason for that is, since they use floating point 16 with this specific location, the most significant bit flips, so the weight changes dramatically. However, with other locations that map to the mantissa, there were hardly any effects. So the vulnerability there is way lower. They also tried floating point 32 location weights instead, and there weren't any bit flips that mapped to the exponent. But again, future work could easily find more bit flips, and then that would also be possible to exploit that. And finally, the possible mitigations would be enabling error correction codes, but they are disabled by default because they cause up to 10% slowdown in machine learning and also other tasks. Then you could randomize the virtual address mapping, but that would again cause an additional performance cost. You could also make memory massaging unpredictable by not immediately reallocating the freed part of the memory, but that would increase the memory usage. So it's always a trade-off. And of course, there is a lot of related work on more sophisticated Rowhammer mitigations, but that would be too much to go into detail now. For the conclusion, the paper showed Rowhammer attacks on GPU, and it was the first to do so. They even disclosed the vulnerability to NVIDIA and major cloud providers like Google and Amazon. And NVIDIA requested a half-year embargo before they published detailed results. At the time of writing the paper, they were still looking for a solution. Then they found multiple new techniques on how to exploit GPU memory specifically, like reverse engineering the virtual address mapping, high-rate hammering by using multiple warps, and evading TRR by synchronizing with caps. And finally, they even managed to get a realistic machine learning exploit, so we see the relevance for actual cloud systems today. There are also other possible targets, like browser renderers could be exploited to steal sensitive pixels, or you could even attack the GPU page table. And that's, again, something that future work could look into. Now, to my review of the paper. In my opinion, the strengths of the paper are, of course, a novelty because there's no prior work that has done this. The practical evaluation, they demonstrated the bit flips on actual hardware, so it's not just a theoretical vulnerability. The paper has a lot of technical depth because they had to tackle multiple engineering problems, like reverse engineering the mappings and synchronizing the hammering and all of that. It's really relevant to machine learning cloud environments. And the weaknesses, in my opinion, are that it only managed to flip the A6000 and it didn't find out why. So it's only the specific GPU that they could exploit. And also the ECC is assumed off, which would be a relatively easy fix. So you could say that the threat model in general is a bit specific. And we don't know how broadly applicable it would be. Also, overall, it's quite few bit flips, so you don't have that many ways to exploit it because, for example, they used floating point 16, but other ways wouldn't be exploitable, or also, I don't know if it were stored sparsely or something like that. The reverse engineering of the address mapping depends on noisy timing differences, which might be quite fragile, in my opinion. And also the tenants might be better isolated in real life. But yeah, the new ideas would be that we could find more bit flips and maybe find out if we could target specific memory locations, because now we rely on the victim writing to a location we know has flips. Also, we could study other GPUs and maybe also newer memory types like HBM3 and GDDR7, which often include more in-memory mitigations. We could also try to circumvent error-correcting codes and evaluate other mitigations in general. And we could attempt to bypass better tenant isolation. Now to the discussion part. The first question would be how feasible this attack is under different cloud GPU scheduling and tenant policies. Because in this paper, we looked at time-sliced, where it switches around the tenants, but it could also rent out a GPU to a tenant for all the time, or you could maybe, I don't know, you can also allocate the users to the GPU, but have separate ports to them. So yeah, what do you think? For example, newer GPUs already have in GPU segregation, so it's like separated in hardware and you can't actually access the different memory parts, but yeah.
Well, if I may comment on this, I think it's an interesting question if we think also in terms of memory isolation and maybe how that could help solve this particular problem. Because if multiple tenants don't share the same memory, then you couldn't have an adversarial tenant potentially flipping bits in someone else's memory. So they could only corrupt what belongs to them, quote unquote.
Yeah, that would be the main point, I guess. But I think it would also make a difference if you just isolate them in software, because then you could still maybe attack adjacent regions. But I think newer GPU models already have hardware-based isolation, so there it would maybe be more difficult to do that. Yeah.
Plus, you also mentioned the difficulty it is in like figuring out what is actually adjacent and what maps where. So maybe software isolation would have to face similar challenges if we were to implement that. I guess that also kind of goes into your next question.
Yeah, let's go to the next question. Which part of the machine learning stack should be responsible for protecting model integrity? Like, you could force GPU to have better mitigations, or cloud providers should be the ones that actually enable things like ECC. Or you could also maybe implement error correcting in the machine learning framework, or leave it up to the user if they want to risk this vulnerability, I guess.
I think so for the cloud providers to be able to protect against these, you would definitely have to have some mitigation strategies that are implemented on the GPUs. So those would have to be able to be activated and deactivated. And then if the cloud provider doesn't make it mandatory, then at least they should make it possible for the users to activate those mitigations. And if they don't want those mitigations, then they could potentially have like higher speed on their GPUs. But I think that the users should at least be able to decide that they want to have those mitigations, or should be forced to have those mitigations, because otherwise, if they don't even know about it and they're attacked, and they don't even know why they were attacked because they don't read like papers like this, but only want to implement their ML stuff, yeah, they should at least have the opportunity to be protected against this.
Mm-hmm. Yeah, but I'd say it's often like, for example, ECC faces a significant performance impact. So the average user would probably not want to have reduced performance for the money they pay, and most wouldn't probably read into detail. So I guess you could also force cloud providers to enable it by default, but then you're locking out the users who know more about this and still wouldn't want to lose performance, I guess. So
I guess to comment on the user enabling mitigation thing, there was a similar issue where they would allow the users to, in the BIOS, you could essentially set your DRAM refresh rate to higher. And I remember reading so many complaints on the internet of people being like, why would I possibly do that? My computer is slower and I gain nothing from it. So maybe there is a bit of an attitude of resistance because people are not really aware of the severity of the problem.
Yeah, let's go to the next question then. Should future systems prioritize fault tolerance or fault prevention? Like, you could focus on designing the GPU hardware such that bit flips, for example, wouldn't even be possible. But you could also make the machine learning frameworks more resistant to possible errors. Like, they wouldn't even be from attacks. It could also just be normal errors that show up. And you could make the models more robust by, for example, having the weights sparsely or in a different format in memory or something like that. But it's I guess, a general question of if we should avoid the errors at all or try to handle them better. Any ideas?
I guess the general challenge of avoiding errors altogether would probably mean a radical redesign of a system, maybe, if anyone agrees.
I think for the case of the bits in the models, where flipping them didn't actually affect the result of it, like, you know, the lower half of the table that you showed, I think that's like a problem of the models, right? Because like, if these bits don't matter, why do they exist at all in the model, right? So like in the end, I think fault prevention using the models or like in the models themselves, I don't think that's a good idea, because that would mean that the models have a very low entropy, or like have about a bunch of useless bits where if you flip them, nothing changes. And that sounds counterproductive to me.
Yeah, I guess you could think about if you could use the additional mantissa bits that didn't make much of a difference to instead induce redundancy, for example. But yeah. Let's go to the next question. Would public documentation of internal GPU behavior improve the security overall? Because you'd have more good guys looking at how everything works, and you wouldn't have to reverse engineer, for example, the address mapping to test for vulnerabilities. But on the other hand, the bad guys would also have better tools. Like, should we rely on security by obscurity or not?
I think you make a very important point here. We've seen, even I think in this session, there are papers that show that security through obscurity doesn't really work, because the overhead of just figuring out what's wrong is really high. So in my personal opinion, if more hardware was open source, we'd have a lot fewer issues like we've seen today.
Yeah, I agree. Like we've seen also with software that usually the open source things, like for example Linux versus Windows, you have a lot less vulnerabilities in Linux usually because you have so many more people looking at it, while with Windows it's only the Microsoft security team basically. But I think another point is often vendors don't want to disclose too much because they would give away intellectual property. So I think it's often not a security argument, but that they don't want to give it out, and it's more of an excuse to not publish it. Any other opinions? Well then, thanks for your attention.
It's just